This image shows the classic planetary model of an atom, with a heavy nucleus in the center and electrons orbiting around it like planets around a sun. If you ask someone to draw an atom, they will almost always sketch something exactly like this. But according to the rules of classical physics, this structure is physically impossible. Classical electromagnetism dictates that any charged particle moving in a circular orbit is constantly accelerating, and accelerating charges constantly radiate away their energy in the form of light. As that orbiting electron rapidly loses momentum, its circular path decays. It spirals tightly inward until it crashes directly into the nucleus. If atoms actually operated under these classical rules, every electron in the universe would collapse into its nucleus in a tiny fraction of a second. All matter would instantly compress into microscopic dots. Since the universe hasn't collapsed, an entirely different set of rules must be keeping those electrons suspended. We have to look to quantum theory to understand why objects hold their shape. To see how matter actually survives, we have to shrink down past the microscopic world and travel to the femtometer scale. A femtometer is 1/4,000,000th of a meter, a space so infinitesimally small that the normal laws of motion completely break down. Diving past the molecular scale, we drop through millions of layers of water molecules, pushing all the way down to the absolute perimeter of a single hydrogen atom. We look for a solid electron whipping around the center like a tiny marble. We actually hit a thick, fuzzy, indistinct cloud. This is the Heisenberg Uncertainty Principle in action. It states that you cannot simultaneously know both the exact position and the exact momentum of a microscopic particle. Because of this rule, the electron spreads out into a three-dimensional probability field known as a wave function. The electron isn't flying in a circle at all. It is trapped by the electrical pole of the nucleus, vibrating in place. You can picture it like a sound wave trapped and reverberating inside a closed organ pipe. Down here, a particle existing in a single specific place is a physical impossibility. The electron exists everywhere within this cloud at once, holding its ground through pure probabilistic vibration. Pushing completely through that vibrating electron cloud, we enter the vast expanse of space separating the outer shell from the tiny central nucleus. We normally picture this gap as a quiet, empty void. To understand it, we have to use quantum field theory. Quantum field theory is the framework in physics that describes how particles interact through underlying fields of energy. It reveals that this internal vacuum actually boils with violent activity. This image shows a mathematical snapshot of the quantum vacuum. Pairs of virtual electrons and positrons spontaneously pop into existence directly from the vacuum itself. They emerge, exist for a fleeting microsecond, and then immediately collide and annihilate each other. In their brief window of life, the negatively charged virtual electrons are pulled slightly toward the positive proton in the center, distorting the local space before they vanish again. The empty interior of an atom is a crackling sea of continuous creation and destruction. Navigating through that static, we finally reach the absolute center of the atom. We have arrived at the nucleus, a structure roughly 10,000 times smaller than the surrounding electron cloud. High school textbooks draw the nucleus as a quiet cluster of static red and blue marbles. If we crack open a single proton, we do find its three constituent parts, called quarks, but they are far from alone. Those three stable quarks are entirely submerged in a raging storm of temporary quarks and gluons. Gluons are the elementary particles that act as the exchange particles for the strong force between quarks. This swirling frenzy is glued together by the strong force. It's the physical interaction that binds quarks together, completely overpowering the electrical repulsion that wants to tear the entire nucleus apart. We look for a solid object at the core of matter, but we find a dense, highly compressed concentration of mathematical energy held together by sheer force. Pulling back, we rapidly reverse our descent. We fly outward from the boiling nucleus, back through the crackling vacuum, and out past the vibrating probability clouds. We accelerate out of the femtometer realm, rushing past millions of complex molecules, rapidly returning to the human scale. We arrive back at a perfectly calm glass of water. The liquid feels smooth and predictable. But this stillness is a macroscopic average. It is the aggregate result of trillions upon trillions of those chaotic quantum storms happening simultaneously. The sensation of solid, continuous matter is a trick played on our perception by vibrating wave functions and repulsive electrical forces preventing atoms from passing through one another. Every object you hold, every surface you touch, and the very hands you use are entirely constructed from restless, violently energetic quantum storms.